Hi, welcome to this quick lecture on the rheology of fluids. Rheology basically means the study of the stress-strain rate behavior of fluids. So just as a reminder, this is the full-up stress tensor written in IJ form. I could write it as a matrix out like this. So these are the shear terms, and these terms right here are associated with the compressibility of the fluid. Notice this is the second viscosity here, which might be new to some of you guys, but in order to describe the full-up generalized stress-strain relationship for a fluid, we need this very long, complicated formula. The diagonal terms within this stress tensor are associated with the volumetric deformation, and so if we consider the fluid to be incompressible, then these terms would vanish. And the off-diagonal terms are associated with the shear deformation. And these are the ones we tend to focus on when we initially study fluid mechanics. These are the ones that I'll focus on in this lecture. So these shear terms come from a result of the no-slip boundary condition. If you think about it, you have a fluid that flows down a pipe. It's moving down the pipe, but at the surface of the pipe, the velocity's got to go to zero. So it sets up a gradient of velocity within that flow, and there's shear associated with that gradient of velocity. From a very simple perspective, if you think about, you take a deck of cards and you splay that deck of cards out, basically that's kind of the model that we're thinking of. Each card has friction with the card above it and friction with the card below it. It's the same we have this friction between each individual layer. That friction is the shear stress. So here's the idea. It's the gradient of that velocity, that change in velocity with respect to y, times some viscosity that leads to this friction. It was actually Newton that observed it was the gradient that shear stress is proportional to the gradient of viscosity, the gradient of velocity, and then viscosity was just a term that we threw in there to make the units work. So consider a linear velocity profile. Here it is here. Velocity is equal to some mean velocity times y over h. In this case, this is the Couette flow. So the mean velocity is this top plate being dragged along the top of this fluid layer, pulling the fluid along at its plate velocity. That's an artifact of the no-slip boundary condition. At the bottom of these two plates, the fluid velocity is equal to zero. So you can see that this profile, y is equal to 0, you get a velocity of 0, and y is equal to h, you get a velocity of v. So it matches the velocity profile, and it's linear with respect to y. So if I take this velocity profile and put it into my definition of the Newtonian shear stress, just that off-diagonal term, I can take the derivative with respect to y, and set it equal to 0, and I get this expression here. So for the linear velocity profile, you can see that the shear stress is constant over that layer. The negative sign means basically it's in the opposite direction of the velocity, right? Sometimes that negative sign appears in books and sometimes it doesn't, so it's a little bit confusing, but keep it in mind that that's what it represents. So there's the shear stress profile. Unlike the velocity, it's constant across that entire layer. Now, that's just a simplified linear velocity profile. There are no linear velocity profiles except in that specialized case. Most velocity profiles look something like this. This is the flow in a pipe where you've got some nonlinear velocity profile, nonlinear with respect to the independent variable, in this case r. So this would be the velocity profile for flow in a pipe. It's parabolic. And if I were to take this and put it into our definition of shear stress for a Newtonian fluid, you would get some function of radius. So it's not that it's constant. In this case, it's a function of r, and here it's drawn here. So you can see it's a linear function. All right. So rheology is looking at various fluids, and not all fluids are Newtonian fluids, but we'll start with the Newtonian fluid. I like to relate it back to Hooke's law. So when you think about a solid, you remember Hooke's law. It's exactly equivalent to Hooke's law. Hooke's law says that for a solid, the stress force per unit area that you put on the solid is proportional to the strain times the modulus of elasticity. So here's the strain. Here's the modulus of elasticity, E. For a fluid, it's actually the strain rate. If you look at the units of this, that's velocity over length. So you end up with 1/seconds is the units. That's units of strain rate times viscosity. So just like for Hooke's law, the resulting rheology relationship, or the stress-strain relationship, is linear, and the slope of that line is the viscosity. And here's what it looks like for Hooke's law, where the slope of the line is the modulus of elasticity. So not all fluids are linear. Dilatant fluids actually, as you strain rate them, as you pull them faster and faster, they resist non-linearly. Those are called dilatant fluids, or strain hardening fluids. Strain rate hardening fluids. And then these pseudoplastics are softening, so they actually get softer. And I've listed examples of each one: water, beach sand, paper pulp. There are some non-Newtonian fluids, like I just represented here. Maybe the stress-strain relationship for those would look something like this. So it's strain rate raised to some power n, where n is not equal to 1. There's also Bingham fluids. Bingham fluids, like toothpaste, is a classic example. It's linear, but it requires that you apply a certain static stress to it to get it to flow. And once it flows then like a linear fluid. So toothpaste, it's stuck on the mirror. It'll be there forever because its gravity, its own weight, is not overcoming this threshold shear stress to get it to flow. There's also time dependency when it comes to looking at the stress relationship. So Newtonian fluids are not time dependent. So if I were to put fluid in a bearing, let's say, and I rotated the bearing and I kept the housing fixed, the fluid within that annulus would be undergoing shear stress. And it would be the same resistance, the same shear stress for all time if that bearing were operating at steady state conditions. Some fluids will actually change and strain harden with respect to time, and some fluids will soften, strain harden. So those hardening fluids are known as rheopectic, or thickening, and those softening fluids are known as thixotropic. And there's examples of each. Speaking of viscosity, viscosity in general it's called a transport property because it's not one of the independent variables. It comes from Newtonian's law, which isn't really a law. It isn't really a law. It's an observation that fluids follow this. But it is a function of temperature and pressure. And in general, they're stronger functions of temperature. And it's also interesting to note the difference between liquids and gases. For a liquid, as the temperature increases, the viscosity tends to drop. And for a gas, as the temperature increases, the viscosity tends to increase. So it's just interesting observations to make. All right, I hope you learned something in this lecture, and I hope you try out some of the practice problems.